In popular science circles, there is a widely discussed concept that suggests we can never actually touch anything with our hands. In other words, any physical contact we make is, in fact, not a touch in the literal and scientific sense of the word. What are the most important and key scientific conclusions that we can ultimately draw from this fact? After all, the most important thing here is not the reality that we can't touch an object with our hands or come into contact with something. The most important fact here is actually a different matter entirely. Where did this idea even come from? Why did it become so popular? Well, it became popular for obvious reasons. To some extent, it's a wow effect. And to some extent, if you are completely unfamiliar with physics, if you view such sources of information only as some kind of inspiring source of knowledge, then, in fact, this will really surprise you. It will truly amaze you. Take any object, you won't be able to actually hold it in your hands. This follows directly from the way matter is structured, from the way substance is organized. All matter in its structure contains atoms. These atoms are arranged in a variety of ways. If, for example, it's some kind of metallic sample, then the atoms are arranged in a crystal lattice. If it's a complex organic sample, then there are carbon chains that consist of molecules, and within those molecules there are atoms. And so, essentially, any touch of any object implies that these atoms interact with each other, that these atoms, in fact, must come into contact with each other, that is, approach each other at a minimal distance. To understand what is happening here, we need to recall how physics describes the structure of an atom. Today, the prevailing model is one that resembles the planetary model but is not actually planetary, although the general idea is the same. Essentially, physics describes the atom as a structure consisting of a nucleus with a positive charge and electrons that are located around the atom. These electrons collectively form an electron cloud, and accordingly, they possess a negative electrical charge. So, what exactly happens when we try to bring two separate objects much closer to one another? The countless individual atoms of one object begin to interact quite closely and dynamically with the atoms of the other object. It might certainly seem to our natural senses that when we touch this particular substance or this item, we are directly touching its physical surface in a literal way. Well, why do we think that? It's logical to assume that we think this way based on our experience of the surrounding reality. If we look at any interaction that takes place in the macroscopic world, we always see one object directly interacting with another object. This is pure mechanics, which, strictly speaking, comes from our, I want to say video surveillance, but no, it comes from our perception of reality with our eyes. And this is where things get really interesting. In 90% of cases, or probably even 95% of cases, what we see with our eyes never actually matches reality. The same thing happens here, and it's no coincidence that we recalled the structure of the atom from the perspective of modern physics. We said that there's a nucleus surrounded by electrons, and essentially, in order to touch something, one nucleus surrounded by electrons has to come into contact with, or touch, another nucleus surrounded by electrons. And you certainly do not have to be a genius to understand that this simply cannot happen. The fundamental point to understand is that the electrons surrounding atoms are similarly charged particles. Each of them carries a distinct negative electrical charge, and we remember from basic physics a simple rule: if we have two charges with the same sign, those charges repel each other. Remember this constant rule as well. This Coulomb repulsion, the Coulomb interaction, is often transferred, for example, to human relationships. And people often say that if you are different, you'll be drawn to each other. But in reality, that's complete nonsense, haha. But within the framework of physics, it's very easy to remember, and in popular science, it also sounds really good. And as we remember, negatively charged electrons are supposed to repel each other. This means that atoms, which are surrounded by negatively charged electrons and have a certain electron shell around them, cannot actually touch each other. Moreover, even with this logic, an interesting point emerges. Essentially, an atom is not a solid sphere at all. An atom consists of a shell, and an atom consists of a nucleus. And when we bring atoms close to each other, these shells start to repel one another. Essentially, it is this repulsion that we perceive as the physical sensation of touching something. Those very tactile sensations that you experience every day when you touch a wooden table, touch a phone charger, or touch a cold door handle. All of these are sensations created by our consciousness, based on the fact that there has been a fundamental electromagnetic interaction between two electron shells. And of course, popular science has spun this idea to the point where it claims that we can never actually touch anything with our hands, that we can never truly make contact with anything in our lives. and in essence, that's actually true. Ultimately, it all boils down to the fundamental concept we discussed earlier, specifically concerning visual perception. It's just very hard for us to imagine anything different when we're used to seeing one physical object touching another physical object. It's difficult for us to grasp that the interaction is actually much more complex, like when a sprocket winds a bicycle chain, and that's how the bicycle moves. And if you start thinking in terms of the chain never actually touching the bicycle's sprocket, you'll just start to lose your mind. Especially if you are, for example, a professional bicycle mechanic or something like that, and when the appearance of gaps in some mechanism guarantees the presence of play. And all of this just can't be reconciled with some deep physics that seems completely counterintuitive and nonsensical to you. By the way, even from this, you can clearly understand why purely technical specialists perceive abstract theoretical models as total nonsense, as some kind of fundamental misunderstanding, as a futile attempt to find something that simply doesn't exist, and so on. Because when you constantly work with these kinds of mechanisms and systems where there is precision, it becomes very difficult for you to accept a certain standard physical inaccuracy. But that's not what we're talking about right now. And now we come to a situation where our perception deceives us. It seems to us that at this very moment I am touching this object, but in reality, if we were to look closely right here, in the gap between my finger and the charger with a highly sophisticated and precise microscope, we will see that there is always a tiny microscopic distance between the organism, between the atoms of one system and the atoms of the other system. Moreover, it is extremely ill-advised and dangerous to force atoms to bond with each other. If we assume the fact that if I really were now touching the atoms of this charger with the atoms of my hand, a truly fascinating and remarkable phenomenon would happen, something very, very likely to be highly catastrophic and deeply unpleasant. And for example, we could turn any table we touched into neutron matter, and ourselves as well, but we'll talk about that a bit later. Alright then, let's examine the reasons why, in our physical reality, some atoms cannot touch, come into direct contact, or interact with other atoms, in the manner we experience tactile sensations. The thing is, there are at least two important parameters that we need to take into account. One of them we've already briefly mentioned, it's the electrostatic force that exists between any charged particles. This is the Coulomb interaction, which means that two electrons with the same charge will repel each other. Alright, let's accept that. Let's also mention here that the so-called Pauli exclusion principle prevents two electrons from touching each other, and this exclusion principle forbids two identical particles from occupying the same point in space. Alright, well, we've all heard this many times in physics class, and it's also in those popular science sources that constantly tell us about the impossibility of touching something. But how do these interactions actually work? What is really happening there? This is a very deep and extremely interesting question. In order to understand why this is so interesting and complex, we need to at least take a more thorough look at the reasons behind exactly how all of this works, and how physics explains these processes. Let's start with electrostatic repulsion. To understand the process, we need to remember that essentially any modern particle, a particle at this level, is described as a disturbance in a field. What does this mean? As we remember in quantum physics and quantum field theory, each interaction has its own field. There are many of them, and for each particle, for each phenomenon, such a field has been found. In the case of electrons, this is the so-called electron field. An electron essentially is a disturbance of this electron field. This electron field possesses certain characteristics, and it is also capable of interacting with the electromagnetic field. So we get this interesting situation where we have an electron field with various disturbances in it. These disturbances are essentially electrons, and these electrons are able to exchange, well, perhaps it's more accurate to say information, although the word interact is often used with each other via a virtual photon. The mediator in this process is the electromagnetic field. This is yet another type of field that enables interactions between electrons. That is, electrons, which themselves are fluctuations in the electron field, are able to exchange various interactions with each other through the electromagnetic field. Essentially, this interaction comes down to the fact that we have an electron field that gives rise to electrons and an electromagnetic field that enables these interactions to take place. When we have two peaks of excitation in the electron field, which are electrons appearing close to each other, there is an intense exchange of information via a virtual photon between the electromagnetic field and the excitation of the electron field itself, which, as I mentioned, is the electron. And we observe the process that we perceive as repulsion. In essence, physics describes electrostatic repulsion in such a way that the electron is constantly exchanging virtual photons with the electromagnetic field, And when these two peaks are close to each other, these virtual photons begin to distribute the particle's momenta in such a way that repulsion occurs. Well, of course, it's impossible to provide any material analogies here, and it's also not possible to imagine any mechanical analogies because any mechanical analogy would be incorrect. But I always imagine it as, well, maybe something like a fast-paced game of table tennis, or something closely related to the constant exchange of energies between the balls. Yes, those very balls that mess everything up for us are needed so that we can at least roughly understand what all of this looks like. And if we imagine this as small material particles, as little material balls, which let me repeat is fundamentally incorrect, but necessary just to visualize it somehow, we end up with a simple system. We have one object striking another, there is a certain momentum, and this momentum essentially causes what we perceive as repulsion. In other words, electrostatic repulsion is the process of interaction between the electronic field with its fluctuations and the field of the electromagnet. And there are a lot of different interesting and complex points here that would be worth discussing, but in this particular context, that's not really important for us. What truly matters for us to understand is this: the very interaction that we experience as physical tactile sensations is actually our consciousness actively processing an incredibly complex signal coming from this strange phenomenon. But that is certainly not the whole story. At a deeper, more fundamental level, the Pauli exclusion principle comes into play. This is a much more complex principle, and it's an equally confusing thing. We say that the electron is a fermion, which has a spin. The spin of the electron, well, it's well known. You can find it in tables. It's something like 1/2, if I remember correctly. And this spin is the same for all electrons. The exclusion principle does not allow such particles to exist at the same point in space. So what exactly happens when we try to bring two atoms together? We bring their outer electron shells very close to each other, and as a direct result of this, there must be an event where two electrons end up at the same point in space. Well, what else? How else can you explain it? We are trying to push two, let's say, physical objects together, and for them to push against each other with maximum force, they need to end up at the same point. It sounds strange, but just in case, I'll say it out loud anyway. And when we do this, we encounter a situation where the two objects interfere with each other and cannot occupy the same point at the same time. But why does this happen on a fundamental level? On a fundamental level, it's explained by the fact that two particles with the same spin cannot be at that point together. But how can this be explained on a deeper level than just the mechanical impossibility of forcing one object into a place where another object already exists? And explain it in terms of probability. If we carefully analyze the wave function system for two electrons, we find the remarkable result that when two electrons are in the same position with the same spin, the probability of such a state, according to the calculation equations, is exactly zero. And nature effectively tries to forbid the existence of this zero probability. The equations we use to describe particles inevitably drive us toward the conclusion that yes, this system in such a configuration will lead us to a mathematically zero probability of the process existing. But as we understand, a system that already exists has some unfavorable states if it suddenly ceases to exist. And it turns out that essentially the fundamental laws of nature themselves strictly forbid us from pulling such tricks. And the Pauli exclusion principle is described in a manner very much like this, at about this level. Everything again refers us back to the mathematical framework. The mathematical framework says that the probability of electrons existing in this case is zero. And it's disadvantageous for the system to end up in a state where its existence is zero. Therefore, the specific attempt to place two electrons with the same spins at the exact same point consequently results in us experiencing an incredibly powerful and intense physical repulsion between these particles. And in this way, another principle works, which prevents two systems from merging into a single common point. By the way, it is precisely through the exclusion principle that popular science explanations are given for things like being able to place this object on my hand, or for the fact that I can walk on the floor without falling through it, or that a kettle stands on a table without sinking into it. As a rule, this is explained on a deeper level, not through electrostatic interaction, but through the Pauli exclusion principle. These are the two main principles that exist. These two main principles, to some extent, should help to further illuminate the nature of what happens when objects come into physical contact. The nature of what occurs during mechanical interaction. In fact, there are at least 3 more points that should be considered, but they are quite intricate and multifaceted and rather tedious for us to delve into and discuss right now. All these strange interactions lead to the fact that, as it turns out, we completely misunderstand matter. We frequently and entirely misapply the theoretical models we have to the processes that consistently take place in reality. But before that, let's address another interesting point that has surely come to your mind. What will actually happen if we try to bring two individual atoms as close together as possible? Let's imagine for a moment that we've set ourselves the goal of making them physically touch. No, well, using a finger here is already pointless. Let's say that we've set ourselves the goal of forcing the atoms of these two charged devices to finally come into contact with each other. How would we do that? Well, obviously by applying maximum pressure. And in fact, there are systems in nature where atoms really do start to come into contact with each other, but this event is not the most pleasant one. As a rule, there are three main scenarios that are possible here. At the first stage, when the compression can simply be described as very strong, what actually happens is a 100% application of the exclusion principle, and we sense that the energy of the electrons, which arises from the attempt to place them in the same state, a process forbidden by the Pauli exclusion principle, leads to an unprecedented repulsive force. Well, there's a great analogy here. Take a rubber ball, put it under a press, and you'll see how all of this happens. As long as the structure holds, essentially, the system will resist. And yes, it's a very interesting story. Try crushing a rubber ball. Remember those bouncy balls from the 90s or 95 under a hydraulic press? I'll let you in on a secret. We did this at work, and it's awesome. Unfortunately, I don't have any video left of it. But yes, as a rule, various transformations of matter occur there, and this already suggests that when we apply enormous pressure, all sorts of interesting processes take place. For example, the ball turns into, a kind of rubber puddle. A huge amount of heat is released, everything gets smeared, and what you end up with is something like, well, either jelly or some kind of bitumen or something like that. And if we follow this logic, we understand that, essentially, the system exhibits the properties we expect from it. So, the next point is when the pressure force is just a bit higher than it was in the previous case. Well, what do we mean by a bit higher? Of course, it's not just a bit higher, they're actually at about the level of pressure inside a white dwarf. In this case, we can observe interesting processes related to electrons jumping from one atom to another. In other words, we've shifted the object so much that the atoms are starting to get confused about which electrons belong to whom. And the forces of interaction that exist between electrons and atomic nuclei cause these systems to merge together. If we dig deeper, this leads to various processes like thermonuclear fusion and many other fascinating phenomena. This too is probably a topic for a separate lecture or a separate video. And when we move on to truly extreme forces, the most extreme imaginable in our universe, things get even more interesting. The formation of neutron matter takes place. That is, in neutron stars, essentially everything comes down to two objects trying to make contact with each other. But they are untouchable, as incredibly strange as that may sound. When they are untouchable, a very interesting story unfolds. As it eventually turns out, the attempt to forcibly compel them, to move them together, inevitably results in the complete disintegration of intranuclear interaction. And what happens then? The formation of neutron matter occurs. Under such extreme pressures, protons and electrons merge into neutrons. This is a well-documented physical process. Indeed, such a process exists, and you can see that it has been investigated in great detail. And this is precisely the mechanism by which neutron stars are formed. Those very neutron stars, about which there are also many interesting popular science stories, like what would happen if you weighed a spoonful of neutron star matter on a watermelon scale? Or what would happen if you brought a spoonful of neutron star matter to Earth? By the way, that would also result in a fireworks show? Most likely it would be quite an explosive event, but fortunately neutron star matter isn't sold on any marketplaces, so the system remains fairly stable. In any case, these three states are what would actually happen if we forced the objects to touch each other. This is important knowledge, but there is also something else very significant. This is what I've been trying to lead you to all this time. We're used to perceiving matter as it is. We're typically used to seeing the physical objects around us simply as physical objects. But in reality, when we look closely at the fundamental structure of this matter, and go far beyond atoms, beyond electrons, and even beyond subatomic particles, we find ourselves in a very interesting situation. We see that matter is actually something like a complex electronic matrix. Matter, in its very essence, is described by various underlying quantum fields and by various disturbances within these fields. And any solid object ultimately turns into what we might call, well, a specific type of excitation in a certain medium. And essentially, any object that we consider solid comes down to the fact that we have some kind of interaction resembling the repulsion between magnets. It's extraordinarily difficult to perceive, and very hard to imagine that inside this electric charge there aren't any particles. no microscopic building blocks whatsoever that we could reach, but rather they are simply certain disturbances in fields. This completely revolutionizes what we can imagine about the nature of matter. And these moments, which are slowly and steadily beginning to become clearer in physics, like gaining a deeper understanding of the principle behind electrostatic repulsion or the Pauli exclusion principle. And yes, I mentioned all this for a very specific reason, because it directly affects what we are discussing right now. And so, understanding these principles clarifies for us the rather complex fact that matter is actually something entirely different. And, you have to admit, it's very strange to imagine any interaction as an exchange of virtual photons between various fields, as the probability that a system cannot exist in a certain configuration, and many other things like that. At this point, we're not all that far away from what we've seen in various science fiction movies, where there were simulation theories, where there were different theories reminiscent of what happened in the Matrix, and much, much more. It turns out that the very nature of matter itself is not about the primacy of some material objects. It's not about the primacy of some fundamental and tiniest building blocks, but rather the primacy of something like energy constantly interacting with various different systems. And this brings us to a most valuable idea, that even from the standpoint of modern physics, at the deepest level, matter turns into something that we cannot describe, something like, well, probably an illusion. Just please, don't exaggerate all these ideas to the point of saying, well, okay, if it's all an illusion, then if I fall off a balcony right now, it's all nonsense, it doesn't exist. It's important for us to understand that whatever may be happening at the deepest level, we exist on the material level, and the interaction that a falling apple from a tree has on us, the very same famous apple, which, by the way, is actually a scientific myth. In reality, nothing like that happened, but that's beside the point. All of this is, for us, a completely real event. But perhaps the most important thing you should take away from this video is not the fact that we can never actually touch anything, which is so actively promoted in popular science sources. Probably every well-known popular science channel has had a video exactly like that. And it's not just about the idea that all matter boils down to some mysterious and incomprehensible entities that we can't fully explain, or that breaking things down into the smallest building blocks of matter ultimately leads us to a dead end. The whole point is that matter is actually a very complex and multifaceted object. And the ideas we have, which are shaped by our perception of the world around us, are often not entirely exhaustive or complete in their description. And at a deep physical level, any process we imagine to be simple actually comes down to extremely complex aspects that need to be worked out in detail and with precision. And so in the case of matter, it all comes down to the fact that matter reduces to a state that simply involves some incomprehensible field disturbances, which are hard for us to imagine. It's hard to imagine that the repulsion between two objects comes down to an exchange of virtual photons through the electromagnetic field. You have to agree this is very valuable and it's very important. Why is this important? Because we often touch on such topics on the channel. But now we've provided at least two thorough and detailed logical arguments that confirm that this is indeed how it works. I hope this information was useful for you, comprehensive, and perhaps changed your understanding a bit about what matter really is, and how all of this functions on a much deeper fundamental level. If that's really the case, then I ask you to support the channel as usual by giving it a like. Be sure to like this video because it's necessary for YouTube to, let's say, gradually promote it. This is beneficial for the entire project. And if the project grows, I can devote more and more time to it. You can also support me through the links in the description. There's a lot of useful stuff there, and I think you'll find something for yourself too. Also, I ask you to subscribe to the Telegram channel. And of course, please subscribe to this YouTube channel as well. Thank you all for your attention. I believe that such conversations are very useful and worthwhile. And if you think so too, I've already mentioned what you can do. At the very least, you can like this video. Until we meet again, my friends, thank you for watching this video. Wishing you all the very best and a great mood.